We are now formally recording, sir.
Thought you'd like to get the pictures on there as well.
Okay.
Okay, so find
Bit of a start late, but we're now all here.
yeah, have to get my script back here. That's full. It's in a full screen mode. Let's see. There we go.
That's just breathtaking.
Okay.
Yeah.
Well, good evening, ladies and gentlemen. Welcome to our December general meeting and star party. Our presenter tonight is Hanan Greenberg with his talk As Long as the Sun Shines, which may have something to do with tanning lotion. I'm not sure. It's the third in a series he's put together, two others of which we've enjoyed in August and October. Plus, he's promised us now a fourth one come January titled The Life Cycle of Stars. Hanan is a longtime member of the club, joined back in around 2000, I believe, and I think he served 7 years in a row as our vice president. And though his work and his living arrangements took him out of our locality down to San Jose, he has recently returned to favor us with his presence, for which we're very grateful, because there are two other clubs, San Jose and Peninsula, that he could have gone to, but he chose to come back and favor us with his productions and his participation. Now, as long as the pandemic interferes with our customary face-to-face events, we expect to hold these combination meetings and star parties over Zoom, and may continue to feature them even after our access is restored to CSM and Crestview Park, assuming everybody isn't just sick to death of Zoom. We've been finding it useful to hold our meetings and lectures on the Saturdays closest to first quarter moon, which is not only the best phase at which to observe the moon, but which, because it sets early, avoids having a bright moon in the sky during the following star party, when we're looking for fainter deep sky objects. Now you've been added, I believe, in a microphone muted condition when you first come in. I know I was. But if you have a question or contribution, feel free to unmute your microphone to say your piece. Then please again mute your mic to exclude background noise. There is a raise your hand button, I believe, if you wish to be recognized, or you can use the convenient chat feature if you have a comment to add. Let's see. Our lecture should take about 45 minutes, I would gather, to an hour. Following that, we'll have time for some Q&A. Then we'll move on to the star party, whose images will include lunar and planetary objects, most likely, as well as those of the deep sky. They will be accompanied by a descriptive live narration, which will likely run between 40 minutes and an hour, depending on how much demand there is from the audience. So welcome and thanks for joining us. Enjoy the program. Hanan, it's all yours.
All right. Thank you, Mike, for that introduction. There was a question that came up from Marianne earlier about where to look for Jupiter and Saturn right now in the sky. It's basically, if you're looking at the moon, you should be looking to the right and a little further down from the moon. It would be quite low in the sky right now, so you have some disruption on where you can find it. It's the best time to try and capture it is around 5:30 or 6 p.m. because it's still not terribly low in the sky. It's already pretty low and there's a lot of atmospheric disturbances, but that would be probably the best time to try and see it. So tonight it might already start being a bit late because it'll start setting and getting to really, really murky views. And we still have 2 more days of it getting closer and closer, so you should try and use it. So,
Thank you.
Sure. So having addressed that question, let's get started. Today's presentation is called As Long as the Sun Shines. And what we will be covering in today's presentation is a few topics. We'll talk a little about why does the sun shine and how long will it shine and how do we calculate the lifetime of the sun. As we go through this, we'll share some different theories of the different sources of energy that the sun could tap into, and how we arrived at what we believe today is the correct model. And we'll finish off with a quick overview of the structure of the sun, so we have a better understanding of how it operates. Before I go into the presentation itself, I'd like to take a moment here and say thank you and recognize Professor Richard Pogge from Ohio State University. I subscribe to his podcast, which I highly recommend, by the way. It is a series of podcasts of a series of lectures on Astronomy 101, Astronomy 102, which cover a whole list of topics. And this is one of the many presentations that I heard him give. And I found it so impressive and so engaging that I actually reached out to him and asked him if I could get a copy of his materials and use it for purposes like the ones that we're doing tonight. And he was kind enough to share with me his information. So roughly around 75% of everything you're going to see tonight comes from content created by Professor Pogge and used with his permission. But I just, first of all, want to recognize that, and also again recommend if you're looking for phenomenal podcasts that are quite engaging and easy to follow. I listen to them while driving for a couple of years, actually. They're really, really rich in content and very easy to follow. So with that, let's go into discussing how the sun works. Now, discussing the inner workings of a star is very, very difficult, because all we can observe is the surface area. We're looking at something which is only 1 part in 1 billion of the mass of the sun. So how can we talk with any authority about what's going on deep inside the sun? And there are a few things that we use to conclude what the right model is. First of all, we have a basic understandings of the laws of physics and how gas and matter behave. We can measure some of the external attributes of the sun. We can look at its radius, its mass, its luminosity. We can measure that luminosity, which you'll soon see is very important. And we can use that to theorize what is going on inside. And then, as you see later on, we can also create experiments to test those theories and find out which one of them is right. So we'll walk you through, obviously, all the details. Now, in today's presentation, we're going to touch on a lot of concepts. Some of them are more complex than others. So as Mike said earlier on, please feel free to come off mute and ask a question verbally, which is best, because I won't be tracking chat all the time. You can also send it into chat if you'd like, and we'll try and get to those as well. And after you're done asking your question, please go back on mute. So in today's presentation, we're going to answer one simple question: how long can the sun shine? And we will basically provide a number, but more importantly, we'll try and understand how the sun generates its energy and how we know what that number is, that lifetime of the sun. So let's get started. Stars are big balls of gas that shine because they are hot. The reason the sun shines actually has nothing to do with the way it produces energy. It shines simply because it's hot. Hot objects give off light. If you were to take an iron rod and put it in a fire and pull it out, it'll be glowing red. It's glowing red and letting off that light simply because it is hot. The other thing that's important to understand is that the sun is letting off energy all the time. This shining of the sun, or its luminosity, is actually a way of losing energy. The action of shining is letting off photons. Photons are escaping the photosphere of the sun. And photons are essentially little packets of energy. So essentially all that light, all that luminosity that we see leaving the sun is energy leaving the sun. Now, there is no heat in space, so the sun is losing all that heat and all that light to space. And unless it has a mechanism inside to continuously produce more energy, it will fade out and disappear at some point. So our goal here is to understand what is that source of energy and how long can that energy last? That's what we're going to try and understand in today's talk. Now, to answer basically that question, how long can the sun continue to shine, we need to understand two things or answer two questions. The first thing is, what is the internal energy content of the sun? How much fuel does it have? And the second one is, how quickly is it being lost? How quickly are we losing that energy? Think of it in the context of a car. If you have a car with a tank of gas, and you would ask yourself, how long can I drive this car, let's say 60 miles per hour? You would have to ask yourself, how much gas do I burn while driving 60 miles per hour? And how much gas do I have? And if I were to take the amount of gas that I have, divide that by the rate at which I'm burning it, I would get the answer of how long I can drive the car. Same thing applies with the sun. It's a relatively simple formula. The lifetime of the sun is simply the amount of internal energy divided by the luminosity. And again, the luminosity is the speed in which the sun is burning its energy. We can actually measure it. It's a very simple measurement. You can actually measure the amount of photons you're getting from every square inch of the sun's surface. Because the sun is a ball, we know how to calculate that surface. It's basic geometry. It's 4 pi r squared. So if you were to take that total surface and multiply it by how much energy or photons you can measure from a single square inch of the sun, you can understand how much energy the sun is burning at any given moment. So if you knew the internal content of the energy of the sun, divided it by this rate of luminosity, with this rate of energy that's being burned, we'll know how long the sun burns. Now, when people started getting really interested in doing these kind of calculations around the 19th century, there were only two forms of energy that we really understood back then. There was chemical energy and there was gravitational energy. Chemical energy was basically what happens when I take heat and oxygen and apply it to, let's say, wood or coal, the process of burning. What is happening in that process by introducing heat and oxygen is that we are breaking up the chemical bonds between molecules. And breaking up those bonds is releasing energy in the form of more heat. That is essentially the process of burning. And chemical explosives, which were already around in the 19th century, are simply an accelerated manifestation of the same process. We're looking at an object which has an accelerant in it. If you think of TNT as an example, dynamite. If we take dynamite, we're essentially accelerating the process of burning, of applying heat and oxygen to the material we're dealing with, and we are releasing a lot more energy instantly in a more explosive way. But essentially, at the core of it, it's the same process. We're simply using oxygen and heat to break up chemical bonds between molecules, and that is releasing energy. So that is what chemical energy is, and people were generally familiar with that. The other kind of source of energy was gravitational energy. And people had a pretty good understanding by that time of how they didn't understand why gravity worked the way it does. They didn't have Einstein yet, but they had Newton, who gave a pretty good understanding of what gravity does or how it interacts. It was nailed down in his formulas and the laws. And people had also practical experiences even long before Newton. I mean, you could, see water running down a hill, and you could build a mill there, and that would the water would turn a wheel, and you could use that energy to do work, to do power, to apply power. There was also another form of gravitational energy when people saw asteroids or comets plowing into the earth, and all that kinetic energy was changing into heat energy. So these were the basic sources of knowledge that people had for energy in the 19th century. It was either chemical burning or it was, gravitationally driven energy. So basically, they try to use these thought processes to figure out what is the source of energy in the sun based on what they thought energy would be and how long that could last. Now, if you take the most powerful form of burning, I mean, they tried, by the way, calculating what if the sun was all made from a big ball of coal and it was burning coal in space. Forget that there was no explanation of what was the source of oxygen in space to help that burning go on. That question wasn't really being asked, but they were coming up with relatively puny numbers with their assessments of the mass of the sun And they assumed that there was a ball of coal about the mass of the sun burning, didn't really produce a long number. So they went with higher explosive energies, and they used the most powerful form of chemical explosion that was known at the time. And they applied that. They took that and said, okay, what if we had the sun literally made of TNT? Okay. And all that is burning somehow for a long period of time. And it's producing, so they could assume that there was a certain amount of energy being produced from that process. And they divided that by the sun's luminosity. Remember, this is the rate the sun is burning energy or losing energy. And when they went from
How can you calculate how long the sun will shine? Do you know
okay,
how the sun
and that's
shines?
is that a question?
It's very, very hot.
Yeah.
Something that is hot shines.
Anat,
Okay, give-
you go on, could you go on mute because we can all hear you?
Oh, sorry about that.
Not a problem. So, so basically, we're looking at the total amount of energy that could be produced chemically from very powerful explosives, divided by the luminosity, the rate at which the sun was burning. When they put that in that formula we saw earlier on, it produced a relatively unimpressive number. It produced around 16,000 years. And already at that point in time, geologists knew that the Earth was at least 100 million to potentially 1 billion years old, definitely in the hundreds of millions of years old. And so this created what is known as the age crisis, part one, where what was matching didn't make any sense. We were finding fossils in the Earth illustrating that there was life 1 million years ago, 10 million years ago, 50 million years ago. And to have life, to have plant life and animal life, we know that we need heat and we need energy from the sun. So how could life and Earth be older than the sun? This didn't make any sense. So chemical burning did not seem to be a good source for energy to operate the sun. And in fact, Isaac Newton postulated many years ago, many years before that, over 150 years before that, that actually meteors crashing into the sun and asteroids crashing into the sun, not meteors, sorry, asteroids and comets crashing into the sun would be a great source of energy. And somebody actually ran the calculations of continuous bombardment onto this ball of gas that is releasing energy. And that could also produce about 1 million years of energy. And that is, again, more impressive than chemical burning, but still nowhere near enough to support life and to support the luminosity of the sun for hundreds of millions of years. This just did not make any sense. So along came two other scientists, and these were Lord Kelvin and another scientist by the name of Helmholtz. And they came at it from a different angle. They said, listen, the sun isn't just a solid ball of some material, it's a ball of gas, and the laws of gas apply to how it operates. And this ball of gas, this incandescent ball of gas, which is glowing because it's hot, is held by a balance of two forces. It's held by the balance of gas pressure. You have a lot of molecules of gas pressing on each other and therefore pressing out. And then you have gravity pressing everything in and trying to pull everything down. And a balance between these two things is what's going on here. So let's try and see what that tells us about maybe using gravity as the source of energy. And what they proposed is the following model. The interior and structure of the star is held by the balance of these two forces. They need to be in what we call hydrostatic equilibrium, the balance between the pressure and the gravity. And as long as it's balanced, nothing is happening, nothing will change. Gravity keeps everything, falling down and is stopping from pressure from tearing the star apart. And pressure, the molecules of the gas are pressing outside and pressing against gravity from completely collapsing the structure. And as long as these two are in balance, we have a stable star in hydrostatic equilibrium. Now, what happens, though, is that at some point, when these forces are in balance, there is no change to the state of the star. But we mentioned earlier on that the sun shines. And as it's shining, Well, it's letting off energy. All those photons that are leaving are carrying energy away from the sun, and it's losing some heat. Now, if it's losing heat, ultimately, it's going to lose pressure. And now we get to a point where pressure and gravity are no longer balanced. Gravity has more power or more force left than pressure. And under these circumstances, the star will condense a bit. As it condenses a bit, the sun is smaller, it's more tightly gravitationally bound. And when that happens, what happens is the internal density of the sun goes up. We've contracted it a bit, so everything gets more dense, more hot, pressure increases, and now can balance out gravity. And this process can go on and on. So the model that was suggested by Kelvin Helmholtz was that the sun will lose some energy, therefore pressure will go down, gravity takes over, the sun shrinks a little bit. Because it shrunk a little bit, everything got more dense, heat went up, pressure went up, balances out the star. Now pressure and gravity are balanced again, and then it'll lose more energy to shining and condense again, and that process can go on and on and on. So we're using the gravitational binding force of the sheer mass of the sun to create more heat and shine off more heat. And they took that model and put it into that same formula we saw earlier. So we take the gravitational binding energy of the sun, which is essentially based on its mass, and we again divide that by the luminosity. And all these numbers, you don't need to remember them. They're not critical for the understanding of today's presentation. But they're basically units of measure of energy. Okay, so we're looking at the gravitational value of the energy of the sun divided by the speed at which it's losing that energy, the luminosity. And now when we plug that into the formula, we get an object that can shine this way for 30 million years just by shining off light, condensing a bit, increasing pressure, shining off again. The sun could operate for 30 million years. But by the time that they did these calculations, geologists on the Earth came to the conclusion that the sun is at least 2 billion years old, or the Earth was at least 2 billion years old, and therefore the sun had to be older. So this was a real challenge. This is the age crisis part 2. Now, at the time, Lord Kelvin, who had a somewhat high opinion of himself, basically said, well, the geologists must be wrong. But obviously we know that they were not wrong. And as we moved into the 20th century, with the discovery of radioactivity, we were able to do a lot more measurements of the age of the Earth, concluding that the Earth is about 4.5 billion years old. So there was no way that the Earth with life on it could be that old and the sun could be that young. We could not have a young sun. So this just didn't make sense again. And what was not known at the time to Helmholtz and to Kelvin was that they didn't know anything about the structure of the atom. That was something that came later. So they did not know that there was a whole new type of physics that stars can tap into to generate orders of magnitude more energy than is available from either gravitational binding or from chemical sources. And that takes us into the next phase of the 20th century. In the 20th century, there was the discovery of nuclear energy, and it evolved over time. It wasn't an overnight discovery. It starts actually very late 19th century with Röntgen and Becquerel discovering radioactivity and the pioneering work done by Madame Curie and her husband Pierre that started uncovering other sources of energy that were coming from within the nucleus of the atom. Then in 1905 came along Einstein with his miraculous year, and among other things came up with what is probably the most famous equation in the world, which is E equals mc squared. And there's many things that we can take away from this equation, but the really two important ones that we want to pay attention to is that matter and energy are interchangeable. I can place them in the different places of this equation. I can turn matter into energy and theoretically energy into matter. And the other thing is that even if I were to plug in a very small amount of mass, even if I put in a very small number in m over here that represents mass, when I'm multiplying that very small number, a little bit of mass, against c, the speed of light squared, I'm going to get a huge amount of energy. So what this equation was telling us was that in matter, there is a whole huge amount of energy that is locked up. The second thing that happened, or the third thing that happened in the early part of the 20th century by, it was a physicist by the name of Eddington, he noticed an interesting aspect that 4 protons, essentially 4 atoms of hydrogen, had just a little bit less mass than 1 atom of helium. So if I take 4 atoms of hydrogen and I look at 1 atom of helium, they're almost the same weight. There's only a 0.7%. This is less than 1% difference in their weight. But if I were to take that little difference, again, that little bit of mass, and put that into the Einstein's equation, I would get a lot of energy. And so maybe this could be a source. If there was a way to fuse these atoms together and convert some of that mass into energy, maybe this could be a way for the sun to generate energy. Now, let's first of all put some numbers behind this. If I were to take 1 kilogram of hydrogen and I would somehow find a way to fuse it into helium, fuse the atoms together and create helium, I would get 0.993 kilograms. I would lose basically 7 grams of mass. So out of a kilo, I would be almost with a kilo left, just 7 grams left. Now, if I plug in those 7 grams into Einstein's equation, I'm getting a huge outlet of energy. I am breaking the bonds now, not of chemical compositions between molecules. I am breaking bonds at the subatomic level, which releases more than 10,000 times more energy. This number of 6.3 with 14 zeros doesn't really mean much to us. So let's give an example of how much that energy really is. That 7 grams, which is nothing. It's less than it's not a pencil, it's really heavy compared to that. It's like a third of a pencil. Converted into energy, produces enough energy to take 64 million tons of rock and move it about 3/4 of a mile in the air. That is a huge amount of energy. If I were to take, instead of 7 grams, if I were to take 100 grams, that would be a hydrogen bomb. And 100 grams is still not a lot. That would be a hydrogen bomb enough to level any major city on the planet. Our sun, as it turns out, and we'll talk about that in more detail later, our sun converts 600,000 tons of hydrogen into helium every second. So 100 grams is a hydrogen bomb. We're talking about 600,000 tons converted every second. That is the equivalent of billions and billions of hydrogen bombs going off at the heart of the sun at any given moment. So the question is, it's an interesting theory. How does it work? How do the details of this process work? Before I go any further, by the way, I want to take a quick break here and see, are there any questions? Because we walked through the chemical theory, the gravitational binding theory, and now we're dealing with nuclear fusion theory, and we're going to go deeper into that. But before I go there, let me see, are there any questions from anyone? I'm going to see, I think there's one thing here that came in the chat. Oh, that was just me. Okie dokie then. So I will continue. How does all this work? Okay, sorry, I was stuck there. So the protons don't just bump into each other accidentally. It doesn't work that way. In fact, when we're dealing with hydrogen and we're looking at ionized hydrogen, so it's basically the protons that are smashing into each other. These objects, these subatomic particles, have a positive charge. If you've ever played with magnets when you were a kid, you would take, the two sides that attracted to each other, there was the plus and the minus, and they would stick together. But if you took the other sides, the plus and the plus, or the minus and the minus, they would repel each other. They would actually, you'd feel a repulsion force. Now this force, this electromagnetic repulsion, is extremely powerful. It's in fact 10 to the power of 40 more powerful than gravity. If anyone thinks that gravity is a really strong power, all you need to prove how weak it really is take a small magnet and take a paper clip and attach it to it. And stop and think and look at your experiments. You've got planet Earth with its massive big size and all of its gravity trying to pull on that little paper clip to fall down. And yet a little magnet in your hand is powerful enough to offset all of the gravity of all of Earth. That's how powerful electromagnetic repulsion is. So when I have two protons approaching each other, that repulsion is going to move them aside. They're going to not get close. It has to be really dense and really hot for them to overcome that repulsion. And because of that, we find that only about 10% of the sun, the core of the sun, is dense enough where the protons are so squeezed together and the temperature is so high, around 10 million degrees Kelvin, that they can start moving quickly enough and start smashing into each other before they can repel each other because of the electromagnetic repulsion. And they start fusing. This process is called the proton-proton chain reaction. And in the next slide, I'm going to show you how that works. You can kind of ignore the chemical formula on the left-hand side, and we'll just use the chart to follow how this process happens. So in the heart of the sun is mainly made of hydrogen, and there are this sea of protons, of trillions and trillions of protons in the heart of the sun. And we start with 4 protons, basically, again, this is hydrogen atoms, and we smash 2 of them together. Now, when these protons smash together, 2 subparticles are released. One of them is called a positron, and the other is called a neutrino. A positron is essentially a piece of antimatter. So for those of you who've seen science fiction movies and you hear the antimatter chamber is heating up and all that, it isn't science fiction. It's actually real stuff, and it's happening in the heart of our sun. A positron is essentially a positively charged electron. And once it interacts, once it is ejected from this fusion process, it will interact with an electron and self-annihilate, and 100% of that mass will convert into energy. It is the most efficient energy exchange in the universe. So that is one source of energy. And another source of energy is the neutrino, which is a very small subparticle moving almost at the speed of light, carrying a huge amount of energy with it. And we'll talk more about these neutrinos, but they stream out through the sun, carrying energy with them. So we've smashed 2 protons in the heart of the sun. And the first thing that happened was we created an atom of deuterium, which is a proton and a neutron. And in the process, we released energy in the form of a positron, antimatter particle, and a neutrino, which is a very small particle. We'll talk more about them a little later. Then we have this deuterium, which is this proton and the neutron bumping into another proton. And in that process, they will create helium-3. We have now created an atom that has 2 protons and 1 neutron in it, and we've released a gamma ray photon. Okay, so now we've created that photon that is going to carry more energy with it as it eventually leaves the surface of the sun. And then finally, we'll take 2 helium-3 atoms and smash them together. And in the process, it'll release two protons into the proton soup in the heart of the sun, and it creates a stable helium-4 atom consisting of 2 protons and 2 neutrons. So this is the nuclear fusion process that occurs in the heart of the sun, and in all stars pretty much about the size of the sun, or up to about 1.2 solar masses. Above that mass, it's a slightly different process, which we'll maybe refer to when we come around to the talk on the life cycle of stars. So it's the proton-proton chain reaction starting with protons, creating deuterium, creating helium-3, creating helium-4, and in the process, they're releasing all these massive amounts of energy in the form of positrons and neutrinos, as well as gamma rays or gamma ray photons. Any questions about this process? So far clear, or have I lost people? Okie dokie. I'll take silence as
Clear, you're clear.
all righty, cool. So going forward, let's put this to the test. Does this theory make sense? So if I were to take the core of the sun, okay, the fusion of the core of the sun, as you'll soon see, produces more than enough energy to keep the sun going for a long time. But let's put that into the formula. So when I'm looking at the core of the sun, it's only 10% of the sun. I don't need the whole mass of the sun in my formula. I'm just going to look at only that 10% that is involved in the fusion process. And what is the mass that I have there? And again, look at what that energy value of that mass would be. And then I obviously assume that I'm only converting 0.7% of that into energy. So it's not even that whole number, because it's only 0.7% of that mass that will convert into energy. Produces a big number with 44 zeros. I divide that by the luminosity of the sun. This time, I get an answer of 10 billion years. So now we can see that hydrogen fusion can power the sun at its current level of luminosity for a period of 10 billion years. And because we know that the Earth is around 4.6 billion years, we're assuming that the sun is about a middle-aged sun, somewhere halfway through its life. So that is, you know, the model that's based on assuming that the source of energy is from nuclear fusion. So let's recap on the different energy release comparisons here. The first one was chemical. It was really unimpressive. We saw that it was, you know, it was less than 20,000 years. It was maybe 16,000 years. Whatever you would try and burn, no matter how efficient the chemical burning or exploding would be, it would not power the sun for not even 20,000 years. The other model was the Kelvin-Helmholtz mechanism. And it's one that I'm going to pause on again here, because even though it is not the source of energy for the sun, it actually is a very important mechanism that plays a very important role in the life cycle of stars. And we'll be referring to it multiple times in the talk in January. So that process of the sun losing some energy, or a ball of gas losing some energy, condensing a bit, getting hotter again, and losing more energy, that process actually does occur, and it does have a very important role in the life of stars. It's just not the source of energy that can power it for any materially long period of time. Alone, it would only power the sun for about 30 million years at its current luminosity. However, the proton-proton chain reaction, well, I only need 10% of the sun to allow me to produce energy at the current level of luminosity, at the current rate of losing energy, for 10 billion years. So the key question is, and I'd like to sort of maybe open this to the audience, see if people have ideas, is how would we know? And let me phrase the question this way. When you plug something into your socket at home, you're clearly getting energy. Where is that energy coming from? If you were to follow the power lines and arrive at the power plant, now you're looking at the power plant, how would you know if that power plant is producing energy from burning fossil fuels or from nuclear fusion? How would you tell? Anybody have ideas?
Well, one thing that you could be looking for is neutrinos.
Exactly. So you'd be looking for the byproduct. You'd be looking for the byproduct of the burning. If I were facing that power station and seeing a big chimney stack with lots of air pollution coming out of it, I would know that they're burning fossil fuel. And if I were in front of this building that had nothing coming out of it, but I had a Geiger counter or something else, I might pick up radioactivity. So based on the byproducts, even though I can't see, no one can see what's going on in the heart of the sun, but based on the byproducts coming out from the process, I can test and see Is my theory correct? And as Ken just said, the byproduct we're going to focus on are these electron neutrinos. Now, they're created in this process of the proton-proton chain reaction. What are these neutrinos? Neutrinos are very, very small particles. They are almost massless. They're not massless, but they're almost massless. And they're moving at a speed that is close to the speed of light. And they are beyond tiny. If you were to take a parsec of lead, that is roughly 20 trillion miles of lead. Think about lead, a very, very heavy metal. It has got massive protons, 99 protons in the nucleus of a lead atom. We use them to protect ourselves against radioactivity, right? That's really dense material. And I'm talking about 60 trillion miles of it. And I were to shoot a beam of neutrinos, of 10 neutrinos, 7 of them will come out from the other side as if the lead wasn't even there. That's how small they are and how weakly they interact with matter around them. So, and they don't have any electric charge, so there's no reason for them to interact most of the time, unless there's a direct hit into a proton. They will not interact with the matter around them. So they pass through anything. So the sun is nowhere nearly as dense as what I've just described. Stuff can just pour out of it without any problems. So neutrinos are pouring out of the sun. In fact, in every second of the day, every square centimeter of your body has 60 billion neutrinos just streaming through us. Every day, every second of the day, hundreds of billions of neutrinos are passing through our body from the core of the sun. Within, a few minutes, they just pass through us and we're none the wiser. So they're very small particles. Now, we believe that they're created in the core of the sun because of our theory of nuclear fusion, but if they're so small and they don't interact with anything, how on earth would we detect them? So for that, we've created neutrino observatories. And they're typically, this is one based in Japan. And basically, there are others around the world. There's one, I'm not sure if it's still active. There was one deep in a mine shaft in Minnesota. They're typically built miles below the surface because we don't want the detectors in this observatory to be impacted by any cosmic rays or any other sources of noise that could impact and create a false register. So typically they're buried literally a mile or two below the surface of the Earth. It's filled with 50,000 tons. This specific observatory is filled with 50,000 tons of ultra pure water. And if a neutrino emanating from the sun flies through this and interacts with an atom of this highly pure water, it will release a positron, which will emit a flash of blue light. And in this observatory, there are 12,000 photodetectors that are waiting for those events to happen. And these observatories have been measuring neutrino hits for years. And the data that has come in has shown very clearly that the number of neutrinos that were detected, and obviously we're not detecting all of them. We expect to detect only a small portion of the ones that are just streaming through. But the ones that have been detected are entirely consistent with the rate of nuclear fusion in the core of the sun that would be required to support the sun for about 10 billion years. And there are other ongoing experiments right now that are there trying to get finer results and refine the details. But there is direct evidence that is very supportive of this model of nuclear fusion. So to recap, there were various theories of how the sun can operate and how long it can shine. What we found was that the ones that were based on chemical sources of energy or gravitational binding energy were simply nowhere nearly enough to substantiate a long-lasting sun that would support life for hundreds of millions and clearly now billions of years on the Earth. At the beginning of the 20th century, with more understanding of atomic energy, new models were created that came up with the proton-proton chain reaction, and we've been able to structure experiments that are validating findings that we would expect to see based on what we have hypothesized is going on in the heart of the sun. So Let me take a quick break here and see if there are any questions. We'll go now next into a quick overview of the structure of the sun before we come to the end of the presentation. So it's like 1 or 2 more slides, but wanted to stop here and see, are there any other questions from anyone? Okay, so what is the structure of the sun? This is a decent model which is capturing quite a few things here. Obviously here in the center, that very light blue core, that is the core of the sun. That is where that nuclear fusion, that proton-proton chain reaction is occurring. Now, the rest of the sun is still very tight and very dense. And so it is more efficient for energy to pass through radiation. If you think about a pot, and the pot is very hot, it's letting off heat, but it's not changing its shape. It's still shaped like a pot. It's very stable, but it's radiating off heat. As we go further away from the core, we get into what is known as the convective zone. That is like the water in the pot boiling. So that water is bubbling up and down because it has more range of motion, and there is the transition of energy works easier through convection, or through this bubbling effect, if you will, going on in the sun. So we have the core, we have a radiative zone where energy passes through radiation, and then we have the convective zone where it's through motion that energy is being let off. The photosphere, this is, you can think of it as the underlying side of the surface of the sun. This is where we can see, this is first of all where photons leave the surface of the sun. And when a photon leaves the surface of the sun, it arrives here on Earth within 8 minutes. However, that photon may have been created anywhere between 10,000 to well over 100,000 years before in the core of the sun. If you remember that proton-proton chain reaction, that photon that is created is going to bump into other atoms and get absorbed by them, and then leave that and get absorbed by the next one. And it's very dense material. So it can take as much as 10 to over 100,000 years. And I've heard numbers go as high as 300,000 years for light emanating from the core to finally reach the surface and then make a quick 8-minute dash over to us. So, and you can also see, this is where we would see the sunspots, which are areas of magnetic activity on the sun where there might be a slight difference in the temperature. They're not really black as they appear in the images. It's just that if the surface temperature is 3,000 to 5,000 degrees, and their temperature, because of magnetic activity and material falling down deeper into the convective zone, might only be 2,000 degrees, they appear darker. It's not that they're not hot, they're extraordinarily hot, and they're not black, but to images that we take, they appear darker because of this temperature difference. And then we have the chromosphere, which is where you can actually see, if you're using a telescope with a hydrogen alpha filter, you can actually see surface details of the convection on the surface of the sun. It's also how you would see prominences, which are materials of plasma, really extremely hot gas in a strange state called plasma, which is not exactly a gas and not exactly a liquid, shooting off from the surface of the sun and following magnetic fields and falling back onto the sun. So these are the main components or the structure of the sun. There is also the corona, which sometimes is referred to as the atmosphere of the sun. It's an area where particles of the sun are accumulated along magnetic lines and achieve extraordinarily high degrees, as much as 1,000,000 degrees, actually hotter than the surface of the sun. And while there is a lot of research trying to shed light on it, it's still a bit of a mystery why the corona is as hot as it is compared to the surface of the sun. So that is pretty much what I wanted to cover. I wanted to share with you a couple of pictures I took of the sun. This one was taken back in 2012 during the Venus transit. And this is a white light filter where you can see some really nice sunspots over here and a really big one over here. This is probably 3 times the size of the Earth, if not more. And over here, you can clearly see the clear-cut silhouette of Venus crossing the surface of the sun. So this was the Venus transit of, I think it was June of 2012. And this is an image that I took during the total solar eclipse in 2017, where this black silhouette is the moon, and behind it you can see we can't see the sun itself, but we can see the corona of the sun, and a bit of the prominences shooting out, this little red stuff shooting out from the surface of the sun. And this is the full longer exposure I took of the same event, where you can actually even see some lunar details over here, and you can still see that little flare, that little prominence coming out of the sun. But what is nice here, you can see really the full corona structure that was visible that day. So that concludes my presentation. And again, sorry about the mishap and the transition between the two meetings, but I'm glad that we were able to get everyone together and get through the content. I see there was a question that came in about what is known about the neutrinos that reach Earth. So pretty much what I already shared with you is that neutrinos are pouring out of the sun. They're pouring out in a tremendous rate. As I said, if just through your body, we're talking about hundreds of billions of neutrinos pouring out every day. Actually, it's 100 every second. They reach through the Earth and they pass through the Earth. Again, most of it is undetected. The overwhelming majority of it is simply undetected because they have no electric charge, they're almost massless, and they're moving at the speed of light. They just move through everything and continue on into space. With purpose-built observatories, we're able to detect some of the neutrinos as they interact accidentally with those water pools that I showed earlier on, and those flashes of light that creates is detected by these photo detectors that are installed in these observatories. So hopefully I answered that question. I see there's more questions coming in, so people raising their hands. So please go ahead.
Protuberance versus prominence. I'm not sure which is which.
Well, a protuberance is, so there's a prominence, there's a protuberance, there's a flare, and then there's a coronal mass ejection. These are all different elements, all of them tied to the same thing, which is, this is plasma on the sun. Again, the surface of the sun, it's not a liquid and it's not exactly a gas, it's this plasma material, which has its own set of laws in terms of how it behaves. A protuberance might be just a small change in the structure that is causing a bit of a bump. Whereas a prominence is when you can actually see it shooting out as an arch and then falling out and falling back onto the surface of the sun. A really full-fledged prominence is quite notable and has very
dramatic.
Exactly. Then you have a flare, which is basically a shootout of material, which is most of the time will end up falling back onto the sun, but it doesn't create that nice normal arch-like structure.
Okay.
If it is powerful enough and shoots out strong enough to escape the gravity of the sun, that becomes a coronal mass ejection. Now we're dealing with material that has left the sun and is now going to be streaming out in space. And that is sort of the material that can sometimes cause trouble. Sometimes it just will create nice aurora borealis lights, and sometimes it can really mess up transformers and impact satellites and other things like that. So
Great, thank you.
we definitely don't like them coming our way. Back in, I don't know if you guys remember, in 2003, there was a massive blackout in the East Coast, and there were tens of millions of people without electricity for many hours. I can't remember if it was a day or a day and a half. That was caused by a coronal mass ejection.
Okay.
Any other questions?
Shannon, this is
Yes.
Ed. I was wondering if you could answer two questions.
I'll try.
One of them you might answer next time, but can you give an indication of what the density versus a radio distance profile from the center of the sun is? I mean, I presume it's very, very high in the center, but does it fall off as the thing goes
Yes.
out, or does it stay very, very high until it gets very close to the edge?
No, actually, the and first of all, it differs from one star to the next. First of all, it isn't
Yeah, okay.
it isn't a uniform answer for all
Yes,
stars.
okay.
But if you were to look at a star, for instance, that is in a red giant phase, which we will talk about during the next talk in January, in a red giant phase, the envelope of the star is extraordinarily fluffy. It is, you know, you could, I mean, if you could build a plane or a satellite that could withstand all the gravitational aspects and all the heat aspects of the star, it could easily fly through the material. It would not be very challenging. It would be much less dense than water. But the core itself, and especially when you're dealing with when you start creating more complex cores with heavier matter inside, eating carbon and oxygen all the way up to iron. Now we're talking to things that could be at certain extreme phases 100,000 times more dense than water. And in an extreme case, just before a supernova collapse, it could be 10 billion times more dense than water. So if you're looking at a star that is at its final stage and about to go supernova, and it's a super giant, so the envelope of the star is somewhere out in Jupiter, whereas the core is somewhere down, you know, in where our sun is right now. That core at the very final moments could be 10 billion times more dense than water, while the envelope is still quite fluffy, okay? Much less denser than water. Our sun is more compact in its structure right now. And so the core is quite dense. It's probably tens of thousands of times more dense than water right now, and which is still dense matter. I mean, none of us could go through that. There's nothing that could cut through something like that. But it's nowhere nearly as dense as other scenarios. And the envelope is still, the convection zone, and especially the surface, would be relatively, you could pass through it. Again, setting aside all the heat and gravitational things that would tear you apart. If you could ignore those, it would be material you could pass through.
Yes, okay. And then the second question is, how constant is the luminosity of, or how constant has the luminosity of the sun been, or is there a way that we actually know that?
We actually do know that, and it is measured. And first of all, there are cycles. As we all know, there are cycles to the sun, the 11-year cycle that people talk about. And there are minute changes in luminosity. But if you were to measure it over a period of, let's say, 100 years, those changes, if you were to graph it out, it would look pretty much like a flat line. So you could go and zoom in onto a decade and say, okay, there was a bit of a fluctuation versus the other one, but these are not material big changes in the outputs. We're talking about fractions of a percent. That is not going to stay that way forever. As the sun starts maturing, it is and will continue to start getting brighter. So if you were to measure this not over 100 years, but start measuring this over the next 10,000 years or 100,000 years, there would actually probably be more of a measurable impact into the increase in the brightness. And obviously, if you're going to look at it over billions of years, the sun will get significantly brighter over the next 5 billion years. It's just not something that will, not something you can really sense in the lifetime of a person.
Yes, but historically, is there significant evidence that it was significantly brighter or significantly less bright over a 10,000-year time spans or something like that?
I actually don't know the answer to that one. I think
Okay.
somewhere that, that there was some evidence of some changes to luminosity, and I don't exactly know how they were measured. It might have been in plant life impact and fossils, but I don't remember the details, so I don't want to mislead you.
But do you think it's been significant or relatively insignificant in the scheme of things?
In the big scheme of things, it's insignificant compared to how bright.
Okay. Yeah.
Again, 5 billion years from now, it's completely insignificant. It's not even a 1% change. Where it will be 5 billion years from now is orders of magnitude brighter from where it is right now. But over the scheme of 10,000 years, not really big. Any other questions? Thanks for those, Ed, by the way. In which case, I'll hand this back over to Mike. All yours, sir.
Thank you. That's a great talk.
It was good. Very good.
There's Mike. Mike, you're on mute, by the way, just in case you forgot to come off. Or we may have lost him.
Are we looking for Mike?
We are looking for Mike.
No.
He's there. He's muted.
Let's see if I can unmute him. Unmutate. There we go.
Yeah, I don't know the nature of his computer problems. They're sort of chronic, actually. It sounds like he just needs a new machine.
Yeah. Well,
It's one of those problems that can be solved by throwing money at it.
One of the few.
Yes.
Actually, not that much money. Unless you buy a Mac, you know,
Yeah.
ordinary PCs are kind of almost a dime a dozen.
well, point me to where you can get it for a dime a dozen, man. I could use a dozen. I just bought a new laptop for my imaging, and it sent me back about $1,000.
Ooh, well, that's okay.
Yeah, I
That's,
needed one with enough RAM and enough, I needed a strong core and all that. So one with 16 gigabytes of RAM. So it costs them. Let's see if do we have Michael? I think we've also lost Michael.
No, I'm here just under Lisa.
Okay.
I did disconnect my other computer.
Okay.
I'm here.
So is there any way to contact Mike and let him know that we can't connect with him?
And can call
Yeah.
him.
Yeah, we
No,
can.
call him on his phone.
All right.
And I think I know we would probably be transitioning to our star party, and I believe there's a slideshow that Ken has that we could start with.
Yeah, let me see.
Is anybody calling Mike?
No, you go do it.
Otherwise, I'll do
You
it.
do it. You do it.
Hello? Hello, Lisa?
Hey, Mike,
Hello there.
you're back.
Yes.
Well, over to you, sir.
Well, all right. I guess I've been kind of overwhelmingly tired, so I probably dozed off. Sorry about that.
Oh gosh. Okay.
I'll take that as the critique of my.
No, it was very interesting. Actually, it was
And the good thing is recorded.
followed
There
you
you
up
go.
through all the particle interactions and whatnot. I don't think I missed that much. Anyway,
Okie dokie.
it was quite fascinating. Thank you. So will it be a continuation essentially of the same theme next month? Is that
The next talk will be about the life cycle of stars, and we'll go really into the details of everything from life from a protostar all the way to supernova and the different paths that stars can take based on their mass. And we'll really go into the inner workings. The one thing that we'll leverage from today's presentation is remembering the stars lose energy through luminosity, and the recurring theme of the Kelvin-Helmholtz mechanism in different stages in star evolution. So it'll be a good building block for next talk, for next month's talk.
Okay, great. And I imagine we'll have a short quiz coming up.
There will be, absolutely. And anyone who fails us does not get a COVID vaccine. Sorry, guys.
Okay, so Michael Cook and Ken Lum, have you guys got your EV scopes active, or are those
Well,
online or offline or?
well, what I have is I've taken about a dozen pictures or pictures of about a dozen objects over the last couple of weeks or a week and a half, during the time that we've had decent weather, and we have had some pretty good nights, including the one last night. But what I've done is I've selected out about 5 or 6 objects that that I thought were interesting, and
Okay.
I've turned them into a whatchamacallit, a PowerPoint presentation.
All
Let
right.
me, I guess I have to share the screen to show that. All right. Let me see. Do you
That would
need
be
to do
great.
anything on your side, or I just share the screen for my side? Let me
Well, it's Hanan's meeting, so
Oh,
You
okay.
can just start sharing. You don't need anything.
Okay, let me click on share screen. Oh, here.
I'm hearing a loud buzzing. Is that anybody else?
That humming is from you, Ken. Ken, turn off your computer speakers. You're getting feedback into your microphone on your headset. Okay.
Okay.
You're getting feedback through your microphone. Make sure you turn off your computer speakers. You got a microphone on your headset.
We're getting very loud feedback, Ken, a buzzing
Yeah.
sound. Apparently, there it is again.
You're too close. You're getting it from your speakers.
Yeah, I keep on muting him because otherwise we can't
Yeah, you've got to turn off your computer speakers. It's coming into your headset.
Well, I don't know. Might be something else wrong. I don't know. It's strange that even after muting him, it still kept going on when he unmuted.
Mhm.
Let's see if I can unmute him. Nope, that's not working.
Lean back, Ken.
Yeah, I turned him off again because it's clearly not going to work with the.
No, if you lean forward, it'll. I think that's your problem.
Well, the question is, can Kenny?
Push play from start up in the upper right. Run it as a slideshow.
Again. Ken, if you can hear me, can you try and find the audio? It says, there's a little button there that says unmute, and try and hit on audio settings or something like that and see, or leave computer audio and then reconnect again. That might help solve the problem. It's not in the PowerPoint, it's in the Zoom controls. So you probably have to go to the top of your screen to find the Zoom controls. Not the PowerPoint. Yeah,
I'm going to telephone Ken and see if I can get his cell phone to answer.
Yeah. This is bad.
Yeah, Ken, this is Mike Ryan. Were you able to hear Hanan a couple of minutes ago? Okay. So what's happening is that we're getting a very loud humming sound or buzzing sound, apparently from feedback into your microphone from your computer speakers. So the recommendation is to turn off your computer speakers or unplug them, or go to the top of your Zoom screen and look for an audio button and try and deactivate that audio, because we're not only are we getting that loud humming sound, but I'm not hearing your audio at all. And okay. I'm getting sound through my computer speakers, so if anybody wants to comment or add to what I've just said, Ken should be able to hear you through my speakers. I'm not hearing you over the computer. Now I'm getting background.
Ask him to stop sharing, Mike. The video.
Try not sharing, Ken. Don't share.
Just stop sharing.
Stop your sharing.
I just took it away. So let's see now what happens if I bring back his, if he comes off mute now. Ah, still dead. Well,
You hear that, Ken? You hear what?
yeah, I just killed it again.
Okay, so Hanan took back the control of the screen, and
No, it's back with Ken, so he has control of the screen again.
now then he
But-
turned then he handed it back to you, and we got the buzzing again.
Yeah.
Okay, well, we see your screen. So
What is the yeah, he can't come on there.
I think he'll need to log off and come back on, Mike.
Yeah.
I don't know if people can hear me.
I'm wondering, right now you're playing through my phone speaker. Looks like the call dropped. I was gonna suggest he just speak through my microphone. Lost that. Huh, bizarre. Looks like a nice PowerPoint.
Yeah. Yeah, it's not working. Ken, if you can hear us, perhaps you can just log off the meeting and then log back in. That might be the best way to do it. Just leave the meeting and then join back.
I suspect the problem is the headset with the microphone. You just use the computer speaker and the computer.
Yeah, Ken, this is Mike. The suggestion is that you try logging off the meeting and then log back in. Although,
Okay, all
although
right,
Ed,
let me,
Ed says he thinks the
let me try
problem, Ed,
let me try
although,
that.
although Ed says he thinks the problem might still be the microphone on your headset getting feedback.
I'm hearing the buzz.
Yeah,
Well, let me,
well, try logging
work on
off
it.
and then logging back in. Do you have the login ID, right?
yeah, I think so. Let me see,
That's the 848-8704-5568.
yeah, let me, see if I can, get out of, the meeting. I can't find,
There should
I
be
can't
a
find where
should be a red
I
button.
can't
that's-
find the leave.
Yeah,
Yeah, I know there's a red button, but
it's in
I
the,
don't see it on my
on
screen.
my screen. It's in the lower right-hand corner.
Yeah, he needs to stop sharing, then it'll be more
That
visible to
clearly
him.
is where it is. That's correct.
If you
Bump the lower edge.
There we go.
Well, let me, okay, now let me leave
okay,
okay, I have left and, let me,
so we're seeing
get
Michael.
back in.
We're seeing Michael Cook's screen, right?
Yeah, I stopped his sharing by sharing.
Yeah.
Yeah.
So I've got
Okay.
just as a little startup, the Great Nebula in Orion
Beautiful.
Mhm.
live at the moment.
Is that
Nice.
live?
Is that live?
That is live.
That is
Yeah.
very nice.
Really?
Yeah, it's really bright. It comes in really quick.
Wow.
all right.
Yes, that is very nice. Thank you.
Okay, let me join a meeting here. Let me see if I still have the, Yeah, there it is. Okay, join. Allow. Meeting. SMCAS. All right. Join with computer audio. All right. Can people hear me?
Yeah, I
Um,
hear you, Ken.
Well, I hear you. I hear you over my phone.
Speaker. Hang on.
I hear you over my phone, but not over the computer speakers.
Okay. Can people hear me now?
Are you people hearing Ken through your computers?
Yeah, we can hear you, Ken. I can hear him fine.
People hear me now?
I hear the.
I hear the buzz again.
Yeah.
Yeah,
Unplug your headset.
I was
I
going to suggest. I was going to suggest the same thing. I think you need to lose the headset.
Yeah, but if that's the only microphone he has, we won't be able to hear him. Ken, do you have a microphone on your do you have a microphone on your computer?
Can you hear me now?
You only hear a buzz through the computer speakers.
Okay, can you hear me?
We
Does
can
anybody
now.
hear
Just
Can you hear a ringtone? No.
Ken, do you have a microphone on your computer? Is it a laptop with a microphone? If you have a microphone, I'm not hearing you through the computer speakers.
we can hear him through the computer speakers.
Oh, do you? Oh, okay.
Yes.
All right. Yeah, Ken, they say they can't hear
Which
you.
is amazing because he's muted right now.
Yeah, because it's coming through the phone on Mike's phone. So let's
Yeah, I think we're hearing him through
Yeah,
Mike.
I think we're hearing him through the phone.
That's all I'm hearing.
Mike, are you talking to him on the phone?
Nobody is hearing you except through my phone.
Maybe we should just do that. Just Mike hold his phone up and they talk through that.
No, wait a minute. No, Mike,
Yeah.
hang up your phone.
Okay. Okay, I'm gonna hang up my phone, Ken, and we'll see if we can hear you.
Yeah, hang up your phone. That could be causing the feedback.
I don't think so.
I
Okay,
don't
I've hung
think
up.
so. It started
Still
before.
feeding back.
Yeah, you're right, it did.
I can't hang.
We're getting it and Ken is still muted.
Ken, I was trying to call you again, but now the call is forwarding to your voicemail. So I don't know if why it is that your phone's not ringing. This is Mike Ryan. But again, the suggestion was if you have a laptop with a built-in microphone, you can try disconnecting or unplugging your headset and see if your voice through the microphone will do.
I have the Crab Nebula coming in. The
Yeah.
famous supernova remnants. I think from I think it was ancient China has wrote about it when it came in. If I'm thinking of the right one.
Yeah, it's 1054. Looks
Yep.
great.
M1.
Yep, M1.
Some people say that it happened 1,000 years ago, but actually it's located 5,000 years away from Earth. So it actually happened many thousands of years ago. We only 1,000 years ago here.
Yep, 1,000 years in our known history, not in the actual existence of it.
Yeah, that's beautiful. You know, the star. I understand that the star near which the Crab Nebula is located is, I guess that's the western horn of Taurus the Bull. I used to know the name of that star. The eastern horn, the trailing horn, I think, is called El Nath, and it points the way directly out of the galaxy, opposite to the center.
Yeah, the diagram.
Share now a map, and you can see the red circle of where the Crab Nebula is exactly.
Yes.
And then you can see this is Taurus with the bull. So that's actually, that little circle is where we are in the constellation that we're looking at.
That star had a really interesting name. I'm trying to remember what it was.
Mm-hmm.
Yeah, it looked like a symbol, a theta or something.
Michael, are you located outdoors or are you
I'm in my bedroom.
operating remotely?
I'm in my bedroom. My telescope is out
the ceiling.
is out my backyard, and it wirelessly connects to my iPad, and then I connect my iPad into the Zoom.
That's good. Then you're nice and warm.
I'm nice and warm. Yeah, I learned from Bill, watching Bill do his astrophotography at the Golden Gate Star Party, and he had this, great RV and nice and warm and drinking hot chocolate in there. Meanwhile, all his equipment was outside. He was wirelessly doing everything. So yeah, that's what I want.
Which Bill is that? Bill General?
Bill Lockman.
Okay.
Oh, no kidding. Never seen him do that performance.
Oh yeah, it just he had all his great equipment going and everything, but it was all controlled inside the nice warm RV.
Awesome. And where did he do that?
It was at the Golden Gate Star Party like 2 years ago.
Ah, okay. Golden Gate Star Party. Is that the one up near
like Oregon and Nevada border on the
Golden State.
Golden State, yeah.
Yes.
That's the one. Yep. That was a great very great adventure for the Cook family there. It's really starting to come in better now. You can almost see a little bit of the color of the red on the left side.
Yeah, that is developing nicely. And it's really quite clear. Ordinarily, that's such a faint object, very low surface density visually.
Yeah.
Oh, someone's come back.
Yeah.
Reminds me of the Peter Pan legend with the crocodile with the tick-tock clock inside. You could always tell when he was coming around because you could hear the clock ticking.
Yeah.
Oh, he had gobbled it up or something?
Yeah, that's right.
Yeah.
He ate the clock.
Okay, he's taken off the earphones. Oh, he's putting them back on.
He needs another microphone for his computer. I'm using a standalone mic here. I used to try to use headphones with this desktop, but it doesn't work.
Michael, why don't you show us Mars?
Might have trees blocking Mars.
Oh, okay. I can see it. It's very, very red looking.
Yeah, it's definitely up there. Unfortunately, where I've set my telescope up, it's trees for me. I have to move the telescope around the other side of the tree
okay.
to be able to see
All
Mars.
right. Forget it.
The planet trees, huh?
Hanan, I've been looking at targets all day. You've got a target on your back.
Yeah. Yeah, I'd be jumping in, except I got a problem with the app for my AV scope and I can't get it to work right now.
They just issued a new one for the iPhone today.
Yeah, whatever happened on the Android, it just won't work. If I go to selection, it just crashes. I put a help request in for it, but it'll be till Monday before they get back to me.
Yeah. The previous one they had a bug in it where it crashed on iPhone, but they fixed it in a couple of days.
Oh yeah, I don't doubt they're going to fix it. It's just I discovered it last night.
Yeah, that's unfortunate.
Yeah, and I know our friends in France aren't working on the weekends.
Yes, of course. Yeah.
And it failed on.
Not on Sunday morning, which it
Yeah,
is now.
I failed on 2 different Android devices of mine, same way, identically. So I know they got a problem in the app. It's not something I did to the device.
Yeah, I'm sure.
Yeah, I'd say I've got a tablet and a phone I use to run the scope. Both of them crashed exactly the same place.
Yeah, that's what happened to me last time with the iPhone. I have an iPad and a phone I use, and neither one of them were happy. But it was only in relating to uploading the data, so it was still usable.
Yeah.
I just couldn't get the data off. Once I was filled up, I was done.
Mm-hmm. Well, I've tried all sorts of things, resetting the app, clearing its caches. Actually uninstalling it and reinstalling it, none of that's worked.
This should be the Running Man Onision Nebula, since we're sort of in the time of Orion. I'm hitting a lot of the Orion objects here. And it's going to take a little bit to come in, but they'll start to come out.
Running.
Yeah, the Running Man's going to take a while to get visible. It's a dark nebula in the middle of that.
Yeah, you can see the blue where the emissions are, and then then you'll see the dark area where.
Yeah, I've got a picture from earlier in the year of it, but I just looked, it was 13 minutes enhancement.
Yeah.
Which nebula is this?
This is the Running Man, or it will be eventually.
Oh, okay. Right next to M42.
Yeah.
Could you try M78?
Yeah, let me see if I can hit it.
Okay, well, Eagle's going there. I'm going to steal it from him. There's a vision of the Running Man from early in the year, February. And you can see the dark nebula in there. It's the inside here.
What characterizes the form of the Running Man?
The dark nebula. See it?
Oh, I see. It's the negative image.
Yeah. Yeah, it's a negative image. It's the darkness. As far as I can tell, that's what makes the Running Man.
Oh, I see. Okay. So the shadowy legs below kind of crooked to the rear, like he's
something like that.
off
Yeah.
to the left.
Mhm. Yeah, and that's, as you can see, that was a 13-minute exposure, so. Wasn't very long.
Yeah, I think yours looks a lot better. I think you can get you can kind of start to see the shape well about 5 minutes or so, but yeah. The longer the better.
Yeah, I just wanted to show that. Let's go back to your live stuff.
No, I'm glad you did. It's way better. Now I'm trying to do, I'm trying to get what Hanan asked for now.
Ed, that image was a pre-COVID photo.
Yes, it was pre-COVID. We had a few star parties before, one at a school and several.
Yeah, that would have been the one in San Carlos, right?
Yeah, that was the one in San Carlos, at Central School.
Middle school, yeah. You could tell it was pre-COVID because the Running Man wasn't wearing a mask.
Yeah, right. That's how you can tell.
Mm-hmm.
Well, what we're sharing. Let me
Oh,
do
no, that's
this.
Ryan.
There's a
Now
Ryan
that's
Camp,
the Orion Nebula.
huh? M42, yeah.
Again, with
Boy, it's about.
this was actually taken. This was actually from the school.
And M43 is. on
That's the only time I had
10 o'clock
26 minutes.
10
on the
o'clock
Orion
position
Nebula.
is M43.
Yeah. 142. Yeah. Or maybe 42. Yeah.
Now, is that the name of your scope, a Unistellar?
That's the manufacturer.
Yeah.
The scope
Unistellar is the manufacturer.
EV scope. EV
Yeah,
scope.
it doesn't have the name of the scope on there. but it's M42, tells me where it was taken from, and it was February 20th, 2020 for 26 minutes, or February 4th, 2020. Before we lock down,
Lots of nice Christmas ornaments, Ed.
oh yeah, you like them?
Was that the, were you the elf I saw earlier?
Oh, this virtual stuff is just fun.
Where is your elf these days?
What's that?
You have a pet elf, I know, I've seen it.
Oh yeah, the elf, you mean this one? Hi.
No, the one that you bring to the party, the Christmas party elf. Oh, that's an alien. That's right.
Yeah, that's an alien.
So cute.
Here's Santa.
This one looks like a Vulcan kid.
Yeah, it does. It distorts my face to the point of looking like a kid.
That's pretty good.
Yeah, some of these are pretty cool.
I think he gave you blonde hair.
Yeah.
All right, Han. This is M78, but I've got some sort of light pollution issue off to the left.
Okay.
Yeah.
You can see some of the elements of the dark nebula and the blue parts of the nebula, the reflection.
Yeah. Yep.
That's nice. Thank you.
Best I can get at the moment. I'm not sure what it's near that's causing all the extra light pollution though.
Mike, where are you located?
I'm in San Mateo, near the bay.
Oh, you're down by the, that would be,
I'm in the
He's
Shoreview.
off, Norfolk, just off Norfolk Avenue. About
Yeah,
a mile
Third.
south of Third Avenue.
Yep, that's it.
does that get more moisture from the bay, or would the hills get more moisture?
I couldn't say. It does. We do get a good bit of moisture and we get a lot of wind. It's very windy here. Anyway, I will see if I can find a target I can get a little clearer.
Does that M78 have a common name?
Now let me look it up again.
It's not one I've had occasion to look up before.
It takes a second.
I do not see a common name in the description that they provide. It's just one of the dozens of clouds that are in Orion. You know, Orion's just filled with these things.
Okay.
Yeah, as I read it, that's basically what it says. I'm just looking at Wikipedia. Wow. A lot of nebulosity in there, though.
Go back to Taurus.
Oh, Lisa, if you like all those facial distortions, just download the Snap
Oh,
camera. You don't need to use Snap, just download the camera. That will do it. And you can use, Zoom will pick up,
Ken?
use the Snap camera.
Ken? I just had a call from Ken Lum on my house phone, but when I answered it, he couldn't seem to hear me. Strange.
This doesn't feel right.
Ken, are you there? Are you able to hear me?
Yeah.
Is it?
Hey, Ken. Oh dear, that may have been the problem to start with.
What's that? What is that, Ed?
Okay, just a second. Now let me turn off my microphone for.
Are you able to hear me, Ed? Ed, are you able to hear me? Hello?
Yeah, I see you now. So, okay, so we can get off the phone before we start a feedback. there. Yeah, we could get a strange.
Okay,
feedback
can you hear me?
right on
Can you
the
hear me
phone.
now?
Yes.
Yes.
Okay, good. Okay, good. So,
Woohoo!
wow. Well, what happened was my router got turned off, and I had to unplug the router and reboot it, and then I had to turn my computer off and reboot that, and so now I'm finally back in service. But it took a while to do that, of course.
Yeah,
Oh.
it's not fast.
Okay, and of course the timing was excellent. All right, okay. Let me see. Now, I don't know. I guess Ed, you did a presentation on your stuff.
And no, Michael's live, so he's been showing stuff.
Oh, okay,
Um,
okay. Oh, I see. Okay.
I
That's
was
fine.
showing a few old things just because we hit a dead spot.
Okay. Well, anyway, why don't you finish what you decided to start, and when you're ready, I'll get started.
Are you able to hear my voice?
Yes, I can hear Mike. Mike Ryan. I can hear you now.
Okay. I think you just called my home number.
Yes, I did, and that was because because
when
I had to reboot my computer.
Okay. When I picked up, there was I couldn't hear you speaking. So
Yeah,
yeah.
I have hung up on my landline right now.
Okay. You also have
he called me and I
you
gave
have
him-
my cell phone as well? My cell phone
Yeah,
number?
I should. Let me
That's
see.
that's what I had called you from before.
Oh, I see. Okay.
Okay. Okay.
Anyway,
Mike's
but we're
Michael's
back
coming in
on.
with another screen.
Okay.
Yeah, I have your cell phone.
Cigar
It's
Galaxy.
678-2762. Okay.
That's the one. Yeah.
All right. Okay. But looks like I'm back on. So
Yeah,
I'm-
he's on.
Yeah.
Okay.
You're
So
on,
just go,
Ken.
okay. Just go ahead and finish what you started.
We'll
and,
do this. This will be the last. This will be the end of the live stuff. But I have the Cigar Galaxy sort of coming in at the moment.
Good.
Mhm.
M82.
Yeah, that's a very nice galaxy to get. You can see it's a galaxy.
Well, it's nice, but a lot of people complain it stinks up the place.
Well, it's called cosmic dust.
Yeah.
Yeah.
Well, cigar,
Yeah. Right.
cigar smoke.
Well, cosmic dust is supposed to be about the consistency of cigarette smoke, actually, or cigar smoke.
Is it really?
A lot
sooty.
thinner though.
One of these days we'll come across the pipe cleaner galaxy.
Oh, gosh. I have a few real pipe cleaners, but not. Although I don't
I do.
smoke.
I still have some left over from
Yeah.
the olden days,
Yeah.
Yeah.
And
college days.
a little bit of that sandiness in the background is light pollution.
Yeah, it's a fairly early image. It's so not great. Actually,
Yeah.
seems to be struggling a little bit, but gets you an idea. You can kind of see there's a little break in cloud dust in the middle that you can kind of see. That's sort of prototypical of this galaxy. But I guess
That's the cigar band.
yeah, the cigar band, exactly. But I gets the idea, I guess, across at the moment. If Ken's ready, Ken, you can just take over the sharing at any time you're ready.
Okay. Let me see.
Just
Wait
press
while I plug my ears.
Okay. I hope that won't happen again.
Mhm.
Okay. Let me share. Oops. This will stop the other screen share.
Yeah, that's fine.
Yeah,
Just-
share
That's okay.
screen.
Continue.
Oh,
All right. Okay. And then let
Yeah,
me
it'll
go over
knock him
to.
off.
Okay. Can people see that?
No, not yet. You gotta share.
still
There
saying-
you
Oh,
go.
yeah.
Okay. You got it?
Yep.
Okay,
Yep.
good. All right, good. All right, so now these are pictures that I took over the last week and a half, so these are not live, but let me see if I can go to the slideshow and start
Mhm.
from, I'll just show a few of these pictures. This is an interesting this is actually an interesting galaxy. I've been working off the, I've been working off of the I had some notes here, but I don't know what happened to them. Oh, there they are. They fell
Oh,
down when
there
they
was
fell
one on
down
your,
when.
there were notes on your PowerPoint screen.
Oh, well, yes, there were, but I can't see them on my screen from my side, so I had to print them out, and
Yeah.
the paper fell down while I was struggling with my computer. Anyway, I've been working off of some of the observing lists that Sue French has published, not only in her monthly articles in Sky and Telescope, but also from her book Deep Sky Wonders. So I'm just going to show maybe half a dozen objects here. This is an interesting galaxy. It's actually quite nearby. It's only about 10.7 light years away. It's called IC 342. It's in Camelopardalis, I believe. Yeah, it's Camelopardalis. This is but despite its relatively close proximity for a galaxy, it's actually extremely faint. And the reason for that is because it's located in line of sight near the galactic plane or the galactic equator. And so as a result, the dust from our galaxy, the Milky Way, is blocking a lot of the light that is coming from this galaxy to us. So even though the galaxy is actually quite large, it's quite faint. So you can see a fuzzy core in the center of the photograph, but you can see faint hints of the spiral structure of the rest of the galaxy covering most of the central portion of the photograph.
Yeah,
And
you're right.
so you can just barely see it, and
That
that's
is
because there's so much light extinction due to the dust in our galaxy due to the line of sight of the galaxy from us. Now, now just notice this line of stars above the nucleus of the galaxy, and I found on the internet a more enhanced view of this galaxy. And again,
wow.
you can see and you can see the full extent of the galaxy. Now, this galaxy at its distance subtends something like a quarter of a degree to a little more than a quarter of a degree, just about half to 2/3 the diameter of the moon. And so in terms of its apparent size, it's actually the third largest galaxy that we can see from here on Earth, superseded only by M31 and M33, which are about 2.5 million light years away compared to 2.7 or 10.7 light years away for this. So this is a very faint galaxy, even though it's close by, and it's acquired the nickname the hidden galaxy as a result of its difficulty of view.
Is this considered to be in our local group?
I'm not sure. I didn't see when I was reading the references on it. I didn't see that that this was classified as part of our local group, but I don't know what the distance limit is for the definition of being included in the local group.
Yeah, sounds like it might be a little far away.
It might be a little bit far away, but it's actually not that far away. But the local group probably goes out only to about 5 million light years.
Yeah.
And so that would include M31 and M33, which are 2.5 and 2.7 million light years away. And then, of course, there are the dwarf galaxies that are floating all around us that are within that sphere. But I'm sure that the people who processed this image probably had to go to an extreme feature in their Photoshop to bring out all the details, because on the EV scope this is all we can see, and you can only get a hint. You can only get a hint of the rest of the galaxy, and you can see how large it is. This is a full field of view of the EV scope, and I haven't defined how big that is. I have to look it up.
I've shot this one for like an hour, and you can get a much more resolution, and I have a good shot of this where you can see a little bit more of that definition, because it was just, you had to just sit on it for like an hour though to get it to come in.
Yeah, but I only let it go for about maybe 10 minutes or something like that. Yeah. Okay, so that's one. Then this is a interesting planetary nebula. This is NGC 1501, also in Camelopardalis. It was discovered by William Herschel in 1787. And it's called the Blue Oyster Nebula, and its distance is about 4,240 light years away, and it's got a very prominent central star. I've had a sort of some questions about the origins of the colors of planetary nebulae. It turns out that the first person to do a spectroscopic examination of any kind of astronomical object was William Huggins, and he did it on a planetary nebula called the Cat's Eye. And what he found was an emission line at about 500 nanometers, which was not corresponding to any emission lines from any known substance at the time. And so at the time, they thought that kind of like helium later on, that they had discovered a new element that only existed in planetary nebula. And so the situation sat for many decades until the 1920s, when until the early part of the 20th century, when Henry Norris Russell of the Hertzsprung-Russell diagram came up with the idea that maybe these are due to emissions from conventional atoms that were in an unusual state. And it turns out that that there are excitation states that exist only in extremely rarefied gases, and they're called metastable states, and they don't exist when the gas density is increased to a higher level, so that there are more collisions between the individual atoms. And so these colors arise from transitions of electrons in states that only occur in rarefied gases. So the existence of the 500 nanometer emission line tells you that something about the density of the gas that's surrounding the star or whatever sample it is that you're examining. So I thought that was kind of interesting. That's the lesson to be gotten from this picture. This is a close-up picture of the same nebula taken with the Hubble Space Telescope. I'm sorry to say I don't have a space telescope up in orbit, so I had to borrow this from NASA, but they're fine with that. It's not copyrighted.
Did you say this was NGC 1781?
1501, 1501.
1501. Okay.
That's correct. It's in Camelopardalis also, right? Okay, so this is a very interesting.
What was the designation for that other galaxy you showed?
I see. That's IC 342.
IC 342.
Yeah, index catalog 342.
And you said it was called the Shadow Galaxy.
The hidden galaxy. The hidden galaxy. I think it was Harlow Shapley several decades later who tried to determine the extent of this galaxy, because it didn't make sense that this thing would be so close and yet be so faint. And so it was concluded that the dust from the Milky Way was extinguishing the light from the galaxy. Okay, there we go. Okay, another object that I took a picture of, actually I took this one last night, was this barred spiral called in the constellation of Eridanus, NGC 1300, and this galaxy is this has a very prominently obvious bar in it, going through the nucleus, and it's in Cassiopeia, and I'm sorry, it's in Eridanus rather, and its distance is about 61 million light years, and at that distance, it's estimated to be about 110,000 light years across. Again, the Hubble's NASA comes to the rescue with a somewhat better picture, and this is a close-up using the Hubble Space Telescope. All right. So it's just a comparison of what a 4-inch telescope on the ground can do versus what even a 30-year-old space telescope can do. Okay.
What's the designation on that one?
NGC 1300.
GC 1300
That's correct.
Eridanus.
Right. I can send you all this information from my notes via
I think
email.
this one's also like sometimes called Superman Galaxy because it's supposed to look like a big the S in Superman or something.
Oh, that's very interesting. Yeah,
Yeah,
I never
remember
thought of that. Yeah, I thought besides, actually, this is situated quite ideally for us right now to photograph because it crosses the meridian sometime in the middle of the evening presently. So it's about as high above the horizon it's going to get at the present time. So if you're planning to image it, okay.
Very nice.
Yes, and this is a star cluster. Where is this? This is also in Cassiopeia. This is NGC, or this is in Cassiopeia. This is NGC 7789. And let me move this down. 7789. It's something called the White Rose Cluster, which I understand. I think that was listed as an object to look at by the Unistellar group in one of their newsletter emails, and it's also called Caroline's Rose because it was discovered by Caroline Herschel in 1783. It's actually quite a large star cluster, so I'm
that's been discussed in one or two of our prior star parties. But
yeah. And it was noted in one of Sue French's articles that there's a double star located nearby, and that's up here, if you can see that on the upper right. And that's a double star known as Espin 38. I presume that's a list from an eponymous astronomer who discovered this double star and listed it in his own catalog. It's the star cluster is located about 7.6 kilolight years away, or 7,600 light years away. Okay. And let me show one more thing. I don't want to take up too much time. Let me see. Here we go. Oh, here. This is a picture of a trio of galaxies in what is it? In Cetus. The one on the lower left is NGC 1087. Another one up in the upper middle is NGC 1090, right up here. And then there's a smaller one right here. Actually, it's the brighter one of two. That is NGC 1084. And I just thought that it was interesting to get the little galaxy cluster in here. I did find an enhanced image of this cluster of galaxies, and here's the full field in all its glory with a bigger telescope and a bigger camera and more processing time. So you can see 1090 down, 1087 rather down here, which has a very irregular bar running through the nucleus, and then there's a classic spiral. Actually, it's a kind of a barred spiral also, and that's a 1090 up here, and then there's 1084 off to the left side here. So, yeah. Okay, so this group of galaxies is about 80 million light years out, and it's the constellation of Cetus. So I have more stuff, but I don't want to. But I can show that another time. I don't know what you showed earlier, so.
No, that was a good compliment. You didn't really duplicate anything, and you have more to show next time.
Okay, that's good. Yep. Okay, and I will try and take more pictures as more clear nights show up.
Okay.
All right. Let me see if I can log out here. Let's see. For some reason, there.
You're looking for the Okay.
I'll just have to. All right. See, where's the screen share thing?
Well, on mine, it's on the bottom in green. Bottom
Yeah,
row
but
in
I-
green.
But I've got a display of all the people, just with their names on it, and no access to the bottom row. And I'm not sure exactly what's going on here.
Maybe if you control minus your screen, it'll shrink the features so that the outlying
You have to bump up against it or something.
the outlining row may show up then.
Okay,
Yeah.
let me.
And I'm sure Hanan can end the screen share as the
Host.
host.
Oh, there we go. So, okay, yeah, I'm saying okay. All right. Okay. So my screen share is off now.
Okay.
All right.
Yeah, and we see
Okay.
your charming visage
I'm
and your white cup.
back in service. Yeah. Boy, that the router went down just right in time.
Well,
Okay.
we learned something.
Yeah. Okay.
Not sure what went wrong with your router, so I'm not sure. But,
Well, it goes down almost every night around usually around 11 o'clock to midnight.
Oh.
But and I don't know exactly why. It's a Comcast thing, and I don't know what exactly is going on.
Takes a coffee break at the wrong time. Huh?
Yeah. Well, this is the earliest that's ever happened.
I was gonna say that your Comcast router shouldn't be doing that.
Yeah, I don't know what's going on, but I have to
Call 'em up
unplug.
and tell them it's happening and they'll,
I had to unplug it and then replug it and then reboot the
yeah, I know,
whole
but
thing up.
that takes
It's
a
a-
Comcast, that
it's
could
a-
take it 10 minutes.
Took me about 10 minutes. Yeah.
Yeah.
Okay. Well, I'm done for the night.
Okay, well, I guess that ends the show, and thank you all very much for your participation and for your patience. Sorry for what I screwed up. It's we'll have to keep in a little closer contact on the login data next time. And Hanan, you actually had the right idea. The idea was to name give the login ID early enough so it could be advertised for a time. But when we were speaking in the board meeting earlier this week, it kind of, I guess, slipped my mind, and nobody thought to mention. And since you weren't able to make the meeting, we couldn't refresh our recollection on that. And I tried messaging you, but I wasn't able to get a response.
Yeah,
So
my apologies. I
kind of-
don't check my personal email that frequently, so text is always better with me. But
Yeah.
it was fun. Got everyone together eventually.
So I kind of panicked and asked Ed to set up a meeting, but next time we'll know better. Okay, well, thank you all very much, and have a lovely evening, and I hope everyone's doing well and your families are all healthy.
Yeah. Have a nice
Happy
holidays.
Happy
Yeah, have a
holidays.
good Christmas, guys.
Merry Christmas all, and
Merry Christmas,
take
everyone.
care.
for anyone
Happy
who
holidays.
was doing it, happy Hanukkah.
Be
Thank
safe.
you.
Happy
Bye,
belated
everyone.
Hanukkah.
Right. Thank
All
you.
right.
Okay. Have a good night.
Bye-bye.
Thank you.
Take care. Good night.
Night.